Welcome everybody to the Machine Learning Needs Mathematical Optimization online seminar series. Today we have the pleasure of having Juan Pablo Vielma. Juan Pablo holds a PhD in Industrial Engineering from Georgia Tech and is currently a research assistant in the Operations Research team at Google. Prior to that, he has held a postdoctoral assistant as well as associate professor positions at IBM, University of Pittsburgh, and MIT. Juan Pablo has widely contributed to the field of mixed integer linear programming and conic programming, to name a few. He has published in leading journals in the field such as mathematical programming, operations research, management science, and mathematical operations research. He is currently an associate editor of mathematical programming computation, operations research, and operations research letters. And he has received many distinctions. Among others, he has been named by the President Obama as one of the recipients of the 2014 Presidential Early Career Award for Scientists and Engineers. We are very pleased of having you today, and the floor is yours. For the audience, we follow the usual rules. If you have very urgent questions, please post in the chat and I will read them for Juan Pablo, and if not, we will have a Q&A session at the very end. Thank you so much.
Thank you very much. Thanks for the introduction and the invitation. I'm very happy to be here. So today I'll be talking about modeling and duality and domain-specific languages. And basically, domain-specific languages is just like another name for algebraic modeling languages. I just didn't want to have modeling in the title twice. I forgot where to click here. So what's an algebraic modeling language? Basically, it's a computer language that allows you to write down mathematical optimization problems in a way that is natural and similar to what you would write in paper. So for instance, here's an example of a simple knapsack problem and the equivalent code in the jump modeling language. And we can see that one natural way of actually writing down perhaps a knapsack constraint is with a sum. And if we look at the equivalent part in the jump code, it also looks very similar. There's a sum, multiplications, and indices, and a less than or equal. So it's trying to make it as natural as possible to write down things. And I would say for linear optimization problems, at least this is somewhat of an agreement on what natural means. But as we'll see later on, for nonlinear programming, this might not be so obvious. And the modeling language includes, well, the language syntax that tells you how to build the optimization problem, how to describe it. But it also includes a lot of code on the back that basically picks that syntax in which you wrote the problem, translates it to a syntax where the optimization solver can understand, then picks the output of the solver, the solutions, the primal solutions, the dual solutions, and transforms it back to a format that is sort of standard for and solver independent, so that you can actually switch solvers fairly easily. And nowadays, there's like a lot of different modeling language. There's been a proliferation of them with different flavors. So some of them are going to be standalone. Others work on top of a general purpose language. They could be commercial, open source, solver specific. Most solvers actually come in with their own mini language. And in addition, there's others that allow you to use different languages. So there's different solvers, sorry. So there's basically a type of language for every taste that you would want. And it would take several slides to name them all. So in this particular talk, I'm going to focus on the two languages that I've been involved with, which are JUMP and the languages used by OR tools. And I keep forgetting where to switch slides. And just like if you heard any of my talks in the last, I don't know, like 5 to 10 years, I've been telling you about JUMP. So I'll be brief this time. JUMP is basically a modeling language that is built on top of the Julia programming language, which is a general purpose language that was developed at MIT. And JUMP supports over 30 open source and commercial solvers for linear, mixed integer, conic, mixed conic, nonlinear, almost every type of optimization problem you can think of. And it was started by 3 PhD students at MIT and about almost 10 years ago, around 10 years ago. And now, fortunately, we've reached a point where we have a little bit more sustainability. So through NumFocus, we actually have funding from grants and projects that actually help us have like one full-time software developer, Oscar Dawson, working on JUMP and the main things in particular. Some news. So we're going to have the Jump Developers Workshop. The annual Jump Developers Workshop is going to be co-located with JuliaCon this year. It's going to be in July. And April 4th is the submission deadline for submitting talks. And I've been probably maybe 2-3 years been promising, maybe more, been promising version 1 of Jump, and now it really is around the corner. So the release candidate was released on February 24th. So basically that should be the final version, the 1.0 version, unless there's any issues. So if you want to try it out and make sure that everything's working for you, now it's the time to check it out and complain if there's anything that's not working as it should. Or tools. So or tools is also has a modeling language, but it's a little bit bigger. It's besides the modeling language, it actually has some built-in solvers. So GLOP is an LP solver, a simplex solver. CPSAT is a constraint programming solver, and PDLP is a first-order method for linear programming that was actually developed quite recently. And this is more of like a multi-language platform, so you can back-end code is usually C++, but you can call and model things in C++, Python, C#, and Java. And this is actively being maintained and developed and actually used by Google's OR team, so it's also fairly stable. And as I mentioned, PDLP is a solver that was added fairly recently. And the news here is like the modeling language used in OR2 was aging a little bit. It was not as friendly as it could be. So what we're working on now is developing a new modeling language called MathOpt that should also be coming soon. And I would say like in a few months it should be available. And again, it's also open source and free to use. Keep forgetting where to click for the slides. Here we go. So as I mentioned, for linear optimization, sort of what is natural or what is it that we want to write down the model as is fairly clear. For nonlinear, things are a little bit more complicated. So the way that I like writing down a nonlinear problem or an abstract nonlinear problem is this format over here, which is a format where Jump tries to write down problems generically. And it's basically minimizing some univariate function that could be nonlinear or not, subject to these kind of constraints, these sort of function inset constraints. So we have a function that is going to potentially multi-valued, so a map, and we want that image to belong to a certain set with certain properties. So for instance, if the set is the non-positive orthant and the functions are univariate, we recover our traditional sort of nonlinear programming approach. If the functions are affine and the sets are cones, we recover basically paradigm of convex of conic optimization. But we could also have things like linear functions subject to sets that are convex, but not necessarily conic. So one of the things that I'm going to discuss is sets that are bounded and things like intervals, because that allows you to write down things like two-sided linear inequalities. And basically, it's around conic optimization and these two-sided linear inequalities that I'm going to discuss some things. One is going to be from Jump's perspective is, well, sort of like how many cones would you like to have here and how natural it is to model things as conic optimization. And for MathOpt, I'm going to discuss, as I mentioned, we want to get solutions from the solver. So the primal solutions are usually straightforward, but dual solutions might not be as straightforward. And one has some clear contracts to say what a dual solution is, that it will be solver independent. And for linear, even for linear programming, it sometimes can be not so clear. So let me start with the first topic, which is Jump and conic optimization. So just to repeat, conic optimization basically is going to be minimizing some linear or affine function, subject to these affine functions belonging to a cone, a closed convex set that is also positively homogeneous. And usually solvers have some small set of cones that they support. And these could be either cones that are called sort of like inherently or naturally conic, like the epigraph of the Euclidean norm, or the Lorentz, or also called the ice cream cone. If you plot it, it really looks like a cone right away. But you could also have other cones that are sort of found by conifying a set. So the exponential cone is a cone that was sort of constructed so that if you look at the cone and take a vertical slice, you're going to recover the epigraph of the exponential function. And this is a fairly generic way of sort of picking some set that is not conic and put it inside a conic set. And it's fairly standard. In this particular case, it's using what's known as the perspective function or the perspective transformation. But in general, you could potentially pick any set that is not a cone and make it a cone by adding one additional variable. So in this case, it was this variable y. And the question is going to be, well, how many of these cones do we really want to use or not? And how hard or complicated it will be to actually model things with them. I guess the easiest way to discuss that is with an example. So this is an example actually from the tutorials from JUMP that now there's tutorials for almost every type of problem you would like to model and solve with JUMP. So here's a simple, I guess, inspired by data science problem, which is minimizing or maximizing the negative entropy of some distribution, subject to some constraints that we're going to assume are linear constraints. And here we have some nonlinear constraint, some nonlinear function, and in the conic setting, our objective has to be linear or affine. So we need to do some transformations to be able to put it in that format. And we can see the transformations here. They're not too complicated. In particular, we see here that, as I mentioned, the exponential cone, if we take sort of vertical slices, we get the exponential function. Here, what we're looking at is if we take sort of a horizontal function, if we make the last variable equal to 1, then we recover something like the negative entropy. And if we now use that, we can basically pick our objective function, split it term by term by adding an auxiliary variable ti for each term, and then write down the constraints that will force the logical condition that we actually want between the variables and the actual function. And once we actually write down this, say, on paper, everything that's linear will look very similar in JUMP. And the last part, which is this belonging to exponential cone, also will look very similar in JUMP. So we still have like a belongs to, and we just need to know that the exponential cone, what its name is. So not too complicated, but there were a few steps that we actually had to do. Now, what's the advantage of doing this? There's many. I'll mention the main one is that now there's extremely effective commercial and open source solvers for conic optimization. There's at least 15 in JUMP. In addition, there's versions for mixed integer conic optimization. And one of the things that makes these solvers so stable and effective is that conic duality is very powerful and nice. It's very LP-like. So that allows to develop nice and effective interior point algorithm. What is one of the issues is, as I showed in the previous slide, we needed some steps to actually be able to build the model. So given that we only have a handful of cones, it's not difficult, but it's not trivial. I guess the easiest way to describe it is Mosaic has a nice modeling cookbook for conic optimization. So I guess the point is, yes, we need a cookbook, so it's not straightforward, but a cookbook is mostly enough. If you follow a few recipes, you will be able to model almost anything that you want. Some are easy, like the one that I showed before. Some can be slightly more complicated. So let me show you one that is a little bit more complicated if you actually restrict to some sets. So here we have basically, it's also a classical example, which is the optimal experimental design. If you don't know what it is, it's not too important. Basically, it's trying to design experiments to do linear regression and get an estimator that has small variance. And it's sort of a classical example explained in Stephen Boyd's convex optimization book. The key that we want to look at is we have some variables that tell me how many times I'm picking a given experiment. And with those numbers, I can build this matrix over here that is going to be related to the variance or the covariance matrix of my estimator. And I want to make that matrix small. And to make that matrix small, I need to come up with some scalarization of small for a matrix. And one natural way of doing that is saying I'm going to minimize the determinant. But the determinant is highly non-convex. It's complicated to deal with. But fortunately, the log determinant is a concave function of the matrix. So this ends up being a convex optimization problem. Now, I still need to do the transformation, same way as I transformed entropy into the conic form. I need to transform this function of a matrix into conic form. And now, in addition of adding sort of scalar variables like auxiliary variables like t and s's, I basically am adding here a big matrix of auxiliary variables that I need to add. And if it looks complicated and it looks like, yeah, I can't really follow if this is really equivalent to this, yes, this would be one of the things that you would have to read from the cookbook and sort of believe. It's definitely definitely not trivial transformation. So one question is, well, I had this function that I use this sort of like conification of the exponential function to be able to transform it into a conic form. Could I actually conify this function of matrices? And indeed, I can actually almost do the same thing. I can still pick this function of my matrix X, do this trick of the perspective function, and divide and multiply by U, and I'm going to get something that is a cone. So if I use this, I could significantly simplify, do almost the same trick I had before, and avoid all these matrix variables and just have a few of these scalar variables to model this problem. And indeed, JUMP actually provides a cone which is the log det, the conified log det set. Slight difference is just there's a triangle there that's saying I'm only going to look at the upper triangular part of the matrix because I know that this matrix is symmetric. And if we follow, most of the things are sort of simple. I'm adding some auxiliary variables, some linear algebra to just build this. But the hard part is just going to be, I'm going to have some slice of this log det cone. So it significantly simplifies things. And in particular, if you actually are calling a solver that doesn't recognize this particular cone, and it recognizes the cones that we had before, which were basically the semi-definite cone and the exponential cone, JUMP internally will transform everything for you and give it to the solver. And when it gets solutions back, it will transform it back and give you the parts that you actually care. And it will also do the same for dual solutions. And that is sort of explained in detail in this paper, which explains basically JUMP bridges, which are these automatic transformations. So adding extra cones beyond some standard set of cones can actually significantly improve or make it easier to actually do modeling and not having to remember the recipes, because JUMP will just apply the recipes automatically and you don't have to know them by heart. If you know discipline convex perming and CVX, this is a very similar approach. In flavor, I would say it's the difference with DCP is that it doesn't just stay in the conic world, it allows you to go slightly further. But it's basically the same idea of like making these transformations automatically so you don't have to do them by hand. Now, another question is, well, okay, having more cones helps you with modeling. Would having more cones help you with solvers? So most traditional solvers are restricted to symmetric cones, which are basically the linear perming, the non-negative orthon, which is used for linear perming, the semi-definite cone, and the second order cone. And modern solvers like MOSEC add an extra cone, which is the exponential cone that I showed, that allows you to also model things like logarithms, exponential functions, and things like entropy. And the question is, well, do we really need to restrict to these sets? And in theory, at least, primal dual interior point methods don't really need any properties of the cone. The only thing that they really need is the logarithmic homogeneous self-concordant barrier, which, if you know what it is, if you don't know what it is, don't worry about it. It's just there's something extra. There's a special oracle that we need from the cones to be able to use it. In particular, it's not just the barrier. We actually have some specific barrier oracles that we need. And if we have those oracles for the given cone, we can write down an efficient algorithm that will solve the problem. And so what we were, with two PhD students, what we actually looked at was, well, we have all these cones. Could we actually write a solver that will use the cones directly? And that solver is known as, called Hypatia. It's written in Julia. It's purely written in Julia. And it basically is generic in the sense that it can deal with any cone for which you actually have these barrier and this oracle. And Hypatia comes with about more than 20 predefined cones. So everything that JUMP can model, it includes directly. So it doesn't need to do any transformation. And in addition, if you have a strange cone and you actually have the oracles that are needed to incorporate them, you can just pass the oracles automatically and Hypatia will use it. And it's accessible from JUMP and convex.jl, which is the DCP framework in Julia. And it also has some custom interface that allows you to do some other interesting things like changing the precision or using abstract linear operators for the linear inequalities, for instance, or the linear equality constraints. And There's a lot of papers associated for that. Let me just show you one set of computational results. And again, as I mentioned, this problem, we could write it with the locked-dead cone, and JUMP will transform it to a formulation with the SCP cone and the exponential cone by adding these auxiliary variables. So we can solve those with MOSEC or Hypatia directly. And these are the sort of these green lines. But we could also instead deal with the locked-dead cone directly. And the key is, if we do this, our variables are going to be the original variables NPI that we cared about, but all these auxiliary matrix variables will not be part of the solver. So linear systems are going to be much smaller. We're going to use less memory. And in the end, we have a significant increase in computational speed. Partly because at some point, the matrices will grow quadratically. They'll be too big, and we'll run out of memory in trying to solve the linear systems. One comment here is, in this particular example, we're kind of like a little bit faster for the same formulation with MOSEC. That's a little bit of an artifact of the specific formulation. It's very dense, so MOSEC doesn't have is a little bit in trouble because they actually care more about sparse problems. So our conjecture is that that's one of the reasons why we're being faster. So definitely Hypatia for specific problems. The main advantage is actually being able to have a smaller formulation, and that's how we actually can really be slightly faster than MOSEC. In general, if you only have STP and exponential constraints, MOSEC likely is significantly faster than Hypatia. I think this is over. Let's check the slide. Okay, and again, the key is you can build these models with JUMP fairly easily, and you can just try Hypatia. It's open source and free to use as well. So if it works for you, let us know. If it doesn't work for you, definitely let us know. We're happy to try to improve the performance of the algorithm. And we'll see how we're in time. Okay. Okay. So that was very nonlinear in flavor. So I'm going to switch gears, and I'm going to go back to MathOpt and duality contracts. And for the first half, I'm going to go back to the linear programming world with some simpler ideas. So first, let me tell you a little bit about MathOpt. So as I mentioned, is the sort of upcoming modeling language for OR tools. It has a lot of extra features, in particular, better multi-language support. You can compile on the web, you can compile in mobile, so there's some features there. An interesting extra development is it's designed, the modeling language is designed so you can actually do remote solves. So one of the things that JUMP was really well known for was doing solver-independent callbacks. We're going one step further and trying to do solver-independent callbacks, but you can actually do remote callbacks through an incremental. Oh, I guess I saw there's some issues with the slides.
I think I can see them well. Is there? I do not see them. Yeah, sometimes for the audience it helps to re-enter the session. So yeah, exactly. Christoph can see them, and me too, and other people too. So yeah.
Okay,
yeah.
perfect.
So for those who cannot see it, if you re-enter, that should be fine. Yeah, Sylvia and Alberto. Yeah.
Okay.
Yeah, you go
I guess when
ahead,
they
please.
change, it's a little bit tricky, so I'll try to change them slowly. And okay, so actually, I guess I mentioned like doing things remotely is going to be one of the main features of this modeling language. And in addition, we're trying to make an effort on trying to have precise contracts for what solutions are. For primal solutions, it's not so tricky. For dual solutions, it becomes a little bit tricky. And as I mentioned, should be out in a few months. We're just like getting the documentation ready and a few issues. And what I want to talk about MathOpt is these, what I mentioned, dual solution contracts. And two things that I wanted to deal with is dealing with two-sided linear inequalities. So linear inequalities have upper and lower bounds, and also working with incorporating linear optimization, conic optimization, nonlinear, and all of it in one framework of duality that covers everything in a way that is mechanical and users can benefit from them without necessarily understanding what duality is at all. So if you know what duality is, usually you can figure out what the dual solutions are, but we would like to have something that doesn't require to go and learn about duality. So let me start with to maybe clarify a little bit the definition of what I mean by two-sided linear inequalities or two-sided LP. It's basically inequalities that have, again, the upper and the lower bound. And perhaps the one that is the most interesting one is bounds on the variables. If you actually give, when you write down an LP for most solvers, you're going to describe linear inequalities, but bounds on variables are going to be special. You're not going to define them as an actual constraint. You're just going to say, when I define the variable, I'm going to say the lower bound of my variable is something, and the upper bound of my variable is something. And those are going to be special in the sense that they're considered one constraint. And in particular, solvers and simplex solvers will return dual variables. They might return one variable for the upper constraint linear inequality or the lower one. But for variables, no matter if you have upper and lower bounds, or just one of them, they will return one reduced cost. So they really are treated as a single inequality. And the question is, well, if I have these upper and lower bounds, how can I write the dual of this particular problem? And to make things easier, I'm going to focus only on the reduced cost and the variable bounds. So I'm going to make these linear inequalities equalities, and I'm going to go back to the basic standard form problem. Also, I guess two-sided linear inequalities are sometimes called range inequalities, if you have heard of them. So here's a textbook example. Very, very simple LP problem. Again, we have duals associated to the constraints and reduced costs associated to the variables. The standard dual is written over here. The optimal solution is given over here. I can see that the optimal objective value is equal to the optimal dual objective value. And the only thing that is sort of strange is, well, the reduced costs don't show up in the problem, and they don't seem to matter. So a user could ask, well, like, what is this reduced cost the solver is returning? And I guess most textbooks will like argue like, don't worry about them. It's something that simplex algorithm needs to work. You can ignore it. So everything's fine, except if you actually now have upper bounds, which will be very common if you're solving the LP relaxation of a mixed integer problem, for instance. Now the standard dual doesn't work. If we actually look at the solution, we found that the things don't work. But even worse, this is likely going to be apparent to the user when they're writing some decomposition algorithm that picks the dual solutions and tries to write a code. And now the decomposition algorithm is not converging. And they have no idea what's going on because they wrote the dual right. And after you start digging a little bit, you realize, oh, well, I guess I'm missing duals for these upper constraints. And if you dig a little deeper, you realize that, well, actually, the interpretation of the reduced cost, the right one is they are the dual multipliers for either the upper bound or the lower bound of the variable, but it's tricky because they depend on their signs. So I need to do all this logic, and I basically need to understand what a dual multiplier is. And if I do that, then everything's okay. But if I don't understand what a dual multiplier is, this is a very, very complicated to understand bug. So the question is, how can we actually try to resolve this? And as I mentioned, the standard form or the traditional or conventional form will be let the users do the sign logic. And again, if you understand LP duality or duality, it's fairly straightforward. If you don't, it's a little tricky. The approach that Jump is doing is saying, well, everything's conic duality for us. So we don't have these two-sided constraints. It's really just two one-sided constraints. So to handle them, we're going to give you a way of actually recovering these linear inequalities. You just can get a reference to the variable and ask, give me the constraint reference to the upper bound and the lower bound. And then you can ask the duals for those. And you never have to imagine that there are actually these special constraints that actually have two sides and only one dual multiplier. And what we're doing in MathOpt instead is we're going to revive a long-lost version of linear programming duality, which is actually has a piecewise linear objective. And one of the reasons we're doing this is the PDLP solver that I mentioned in its development already sort of extended this piecewise linear dual for quadratic objectives, so it was already kind of natural to use it. But this piecewise linear dual has been around for a long time. It's I actually had it. I would always say that this is something that is missing from LP textbooks, and it's like it always annoyed me that there wasn't like a clear way of dealing with the reduced cost in a systematic way. And very recently, I actually Bob Ford pointed out that this dual, in fact, appears as early as an 81 paper by Rockefeller, And Bob actually has some very, very nice slides that describe this dual and how it relates to primal and dual simplex. And so I'm taking away the textbook. I will call this sort of the textbook description of this piecewise linear dual. But again, if anybody knows of another place where this piecewise linear dual appears, definitely be happy to know. So I want to show you the piecewise linear dual, but to make things simpler, it also works for any upper and lower bounds, but it gets a little bit technical if we have general upper and lower bounds. So I'm going to switch and make things easier by just having a lower bound of -1 and an upper bound of 1. And in this particular case, if I look at this problem, the piecewise linear function, the piecewise linear dual looks like this. First, the reduced costs actually do play a role in the dual. They're explicitly in the dual. They're unrestricted because their signs are going to determine whether they're multipliers for the upper or the lower bound. And the objective is no longer linear, but it is piecewise linear concave. So it's still a convex optimization problem. And if I now go and mechanically compare and plug in the reduced costs that I'm getting from the solver and the dual that I'm getting for the solver in the objective function, I now have exactly what I expected. And again, it's mechanical. I don't have to worry about it. I don't need to understand why these duals are the same. You can just give the formula to the user. They'll plug things, and everything will work out okay. Another interesting thing is that we also get extensions of the natural properties of LP duality that we'd expect, like complementary slackness. But we're going to get a version of complementary slackness that I will call signed, because it will automatically imply the sign of the multipliers. So in particular, the complementary slackness conditions for the constraints is exactly the one that you would expect, but the complementary slackness that relates the variables with the duals associated to the upper and lower bounds, or the reduced cost, is slightly weird. Instead of actually having complementarity equal to 0, we actually have it equal to the function that appears in the objective. And if we look at this particular constraint a little bit more, we'll see that depending on the sign of there's an implication on the sign of the reduced cost, depending on whether the variable is active at its upper bound, in which case the sign is negative. If it's active on its upper bound, it's positive is the active at its lower bound, negative if the variable is active at its upper bound, and 0 if the constraint is not active. So we definitely have if the constraint is not active, the multiple 0, but if the constraint is active, we get a signed constraint depending on which side it was active. And if we combine these constraints with dual feasibility, we will recover automatically a dual solution. And in this particular case, we'll recover a unique dual solution. So we still have a system that we need to solve. It's just that some of the constraints are slightly nonlinear, but basically satisfies all the properties. And now, again, it's mechanical. I never had to mention, well, if the variable is at its upper bound, then sign. It's all implicit in this particular formula. So again, things get a little bit more complicated when we have different upper and lower bounds, but it's not too terrible. And in fact, one way to kind of explain this is by going a little bit extra abstraction level and trying to go and incorporate nonlinear constraints at the same time. And let me see how my time. Okay, yeah, I'm doing pretty well. Okay. And as I mentioned, the second thing that we actually wanted to do is I really like to write down a dual for this generic problem. The real function instead problem where I can incorporate conic, nonlinear constraints, two-sided inequalities in particular, which I can actually model if the function is linear and my set is some interval, and basically anything that I would like to do. And the solution is going to be, we can actually pick this problem if I write down the Lagrangian dual in a special way and process it, we're going to get everything automatic. And again, in a way that's going to be potentially complicated formulas, but it's mechanical. You can tell somebody, here are the formulas for duality. You don't need to understand where they came. You just need to apply them. So here is the Lagrangian dual. And it's fairly general. So I'm assuming here that the functions are differentiable. The objective doesn't really have to be differentiable. It could be just convex, but it's easier to just think about it as being differentiable. The sets have to be closed and convex, but there's no property. They don't have to be count. They don't have to be bounded. They can be anything. And we only have one small technical condition that is sort of like an extra convexity on the set. And again, it's a technical condition that just makes the dual work. And the Lagrangian function for this problem looks very similar to the Lagrangian, to the standard Lagrangian you would imagine, something like a multiplier type of function, but it also has this extra term. And if you know what a support function is, you will recognize that this set is the support function, sort of the support function of a convex set. There's a minus there that does things slightly different. If you don't know what a support function, don't worry. I'll get back. A key is going to be that for a given class of set C, this function can be described sort of in closed form, and you again don't need to worry about this. You can just apply the formula. And we actually can get a dual problem by just doing the usual Lagrangian duality framework, and we get strong duality and weak duality fairly straightforward from textbook convex optimization. So I could just stop here, and this is the dual. But again, this maybe how to use this requires some thought. I'd like to have formulas that are easy for the user. And the user, what do they want? Well, they want to get, if an optimal solution is available, they want to get a proof that the optimal solution is the optimal solution. And maybe if they haven't found the optimal solution, they want to get a bound on the optimal value that can be used to fathom nodes, or they could be used to use a decomposition algorithm, to develop a decomposition algorithm. So let me start with the contract for these lower bounds, which is basically dual feasibility. And again, I'm repeating the standard primal problem that I'm defining, the specific way function, this form of the Lagrangian. And we can check that a dual solution is going to be feasible. A dual solution Y is going to be feasible, set of multipliers Y, if there exists some primal solution that could be feasible or not, that satisfies just a set of linear equalities for the fixed x. A condition on this function that I defined, this sort of support function that I have. And if this is satisfied, if I plug in the x and the y in the Lagrangian function, I get a lower bound of the optimal solution automatically. So everything I have here is like, well, I know the form of the Lagrangian, that's mechanical. If I know f, I mean, f and g are the things that the user gave us, so they should know how to apply them. They should understand the gradient of the objective and the function, so that's also easy or mechanical. The only thing that the user wouldn't necessarily know is this function. They might not see, but they might not know this function. But fortunately, again, for specific classes, we can say, if you have this class of sets, the function that you need to use is this. So for instance, if C is the interval that we wanted for our two-sided linear constraints, the function can be written fairly simple. It's a piecewise linear function with two slopes. And in particular, if I have the -1, 1, which is like what I used in the specific example for linear firming, I get this minus absolute value that showed up in the objective of the LP example. So again, this is the only thing that I would say in the contract that we're giving the user, we need to tell them, if you use this class of constraint, here's the function that you should use. Otherwise, it would not be mechanical. They would need to solve this problem and understand. We can also do something similar for optimality certificates. It's slightly more complicated because, as I said, I wanted to just make the part that is sort of extra knowledge just a function, but we have a weird condition that has the argmax, and it makes things a little bit more complicated. But fortunately, if my sets are either a bounded set or a cone, then we can actually replace this weird thing with basically primal feasibility, the same constraint that I had for primal feasibility, and this stranger way or version or signed version of complementary slackness, which again looks like function times the multiplier. Nothing is so surprising there. I would expect a 0 to here for complementary slackness, but the same way in the LP we had this absolute value constraint, now we're going to have this function s. And if I find an x and a y that satisfy this, and primal feasibility for the x, that is a primal dual optimal pair. And again, it's things that I can check. There's formulas that I can check mechanically. And as I mentioned, this complementary slackness, this generic complementary slackness or signed complementary slackness was exactly the generic or the complementary slackness, the signed complementary slackness that I had in my linear firming example early on. So this sort of like follows naturally for this extra abstraction. And again, this function s becomes easy for conic optimization problems. it's basically 0 or infinity, which is going to make this constraint look like something like the belonging to the dual cone, which is what you expect in conic optimization. And there's other frameworks that also sort of follow naturally from this framework. And we can recover a generic dual that is more conic-like or LP-like if we actually add some constraints, like, for instance, asking for all these functions G be affine. But again, you don't necessarily need the dual. The only thing that a user needs to know is these contracts for what an optimal solution and an optimal dual solution or an optimal feasible solution satisfy, and how you can use it. Basically, to certify optimality or to certify a bound on the optimal solution. And I guess with a little bit extra time. So basically, this is what I wanted to tell. So from conic optimization, I guess the message is, if we actually allow more cones, suddenly you make conic building a lot simpler, and you don't need to worry so much about the recipes. But in addition, if you actually have extra cones, you could also improve solving and solve times for specific solvers, in particular with Hypatia. I started in the second part of the talk, well, what about going beyond conics? So one thing that I didn't answer is, well, what about if I can add a lot of cones, can I also just use convex sets? And the answer is, in theory, yes, and in practice, maybe also yes. There's a solver by Karimi and Tuncel called the domain-driven solver that basically says, same way as a Hypatia said, if I have an oracle, this barrier function for the set as an oracle, then you can use the cone, but it has to be a cone. DDS, the DDS solver says, well, if you also have a barrier, which is the equivalent barrier for convex sets instead of conic sets, if we have that, I can also solve the problem. So you could potentially also use sets that are not conic. I also mentioned that if you have a set that is not a cone, you can make it a cone by conifying it by adding one variable. It's not so clear that that translates the oracles that Hypatia wants or needs in an efficient way, but we have some evidence that it might be able to reduce any cost significantly for a fairly general set of cases. So it's still not clear, should we stay in the conic world with a lot of cones, or should we take the extra step to go to the not necessarily conic set? Now, still preparing to this, well, you might want to use conic or not conic. The thing that we wanted to do a little bit in the second part was having a dual that will cover everything, so the user doesn't really need to worry about how they wrote the problem or what the solver can return. They're just going to get something, dual solutions that they can use in a mechanical form for whatever task that they actually had in mind. And one thing that I didn't mention was this setting, because it's sort of constraint-wise, there's an easy way to transform duals from one setting to another. I could write down a formulation in two different ways. Through this procedure, I can actually get a way of transforming the duals. If I had the transformation in the primal, I'm going to get sort of an automatic dual transformation as well. And I guess the more interesting thing from the LP setting is that this sort of recovers this long lost piecewise linear dual that is inherent. It's strongly used in simplex algorithms. So now you can again sort of not have to go and add the extra step of like, oh, well, for reduced cost, it depends. For reduced cost, here's the formula that you need to apply. And with the generic dual, I didn't mention, there's also in feasibility and bounded certificates. There's ways, more specific or mechanical ways to do decomposition. And as I mentioned, there's also a way to write down, simplify the Lagrangian dual into more sort of like well-known duality frameworks or duality problems. In particular, these S functions that I mentioned are the ones you need to know from the set, also appear in DDS's dual problem, if you look at the documentation, for instance. And I guess I'll stop with a few minutes right here. Thank you again for the opportunity.
Thank you very much, Juan Pablo. It was very, very interesting presentation. So we open the floor for questions that the audience may have. And as usual, please raise your hand. We will give you rights to the microphone and the camera. Yes, so we have M. Kovara, yeah. So Jason is going to give you the rights. Yes, it should now be okay.
Yeah, hi. Just out of curiosity, at the end of the first part, you mentioned the logdet problems and compared Mosaic with with your solver. As far as I know, SDPT3 can also handle the logdet functions. Would it also be better than so? Would you compare it with SDPT3 as well?
I would guess, I am not sure, but it would depend on SDPT3. I guess they will build the matrix, which might be a problem. I'm guessing their linear solver will depend on the size of the matrix, and that again might make it slower on the linear solve that they have to do. So I'm not sure. I would guess that it's still going to be slower, just again because of a memory issue. At some point, you run out of memory and things become slow. One, I guess, comment on that is you probably shouldn't solve the logdet problem with any conic solver, because you could probably again solve it. It's somewhat unrestricted, so you could probably solve it with directly without having to go to conic solvers. So really, the real advantage would be if you have logdet constraints and other constraints, and this is just one of the constraints of your particular problem.
Yeah, but you may have also SDP or LMI as a constraint, and then the logdet just in the objective. Never mind. So I'm just playing with these problems. So I just downloaded Hypatia and I will try it. Thank you.
Yeah. So and again, it would depend on what they do, and I would expect that. So one thing I guess they can comment on also the Mosaic is that if you look at iteration steps, Hypatia probably is going to be slightly slower. So it really is the cost per iteration that is making a big difference. So we're going to solve a linear system that only is going to include the NP variables and the dual variables of the I guess, and some dual variables. If we don't have to add the original these delta matrix variables in the primal system, and they don't show up in the linear system, that is the thing that's making a difference. So if SDPT3 can avoid that, then it could work. And I'm trying to, I think it could, given the, it could just use the objective. So if it can, then I would say it would be very comparable to Hypatia and potentially faster because of the faster iteration count.
Great, thank you. Thanks.
Thank you, Michael. Any other questions from the audience? Remember to raise your hand, please, and then we will give you the rights. Yes, Michel, please go ahead.
So sorry, I see there is no other question. Just a question about Hypatia. Are you planning on further development of that code? Because I just tried it, and it for standard SDP it is slower than Mosaic and some other codes. So are you planning improvements?
We are there. So there are some improvements. I would say there's a few parameters that you could tweak that can make it potentially faster. But in some sense, we're not trying to beat Mosaic on the problems that Mosaic can use. It's more we want to motivate solvers to support more cones, I would say.
Yeah,
so
sure. Yeah.
If you're really going to use the cones that are not supported by other solvers, like the big cones, definitely use Hypatia. But otherwise, yeah, there's already great solvers that do SDP and exponential cones. So, and those require a lot of tweaking that we're so far away that it doesn't make sense. Now, I guess one of the nice things about Jump is that you can try both. You can try all of them. I believe SDPT3 might be. I'm not sure if it supports the objective function. But.
All right. Yep. Thank you. Great.
Thank you very much, Misha.
And this is like, I guess it's like the other thing that I really liked is like he actually could manage to actually download all the solvers and check them right away, which I guess is like that's the nice thing about Jump. Live during the talk, you can install it, use it, and benchmark it.
So good. Okay. Please, the audience, do you have any other questions? I guess the audience is downloading things and trying.
I tried.
I have a different kind of question. So you mentioned that some models where there was a data science flavor. Would you be able to tell us a little bit more about that?
So I guess a lot of we did a lot of examples with Hypatia that are mixture between, they were like just for benchmarking, but a lot of them were inspired with practical things. One that I kind of liked was shape constrained regression with polynomials. So there's a framework for modeling polynomials that is using sum of squares that basically is also can be transformed to an SDP. But the sum of squares cone can also be dealt with directly. One of the things we extended as well is that you can pick this sum of, do sort of like a matrix version or combine sum of squares with SDP cone to basically say, describe the cone of polynomials whose Hessian is positive definite, which means it's the set of, it's an approximation of the sets of convex polynomials. So now if you really want to approximate something with a convex polynomial, these are constraints that Hypatia can deal with fairly easily, and then you could do regression with shape constrained or convex polynomials. So that is one that I guess there's other, you can add things like monotonicity and other things like that. And again, Hypatia kind of makes it so that you don't pay the price for the big formulations of SDP, which is perhaps I would say that was the original direction of doing the first step on making significantly reducing the size of conic problems that another solver also was doing. There's a solver called Alfonso that works on MATLAB that was also exploiting that same idea.
Yeah, interesting. Thank you so much. Is there any other question from the audience? I think the audience is tremendously happy with your presentation. So yeah, so we would like to thank you again for coming today, making time in your busy agenda. And yeah, to the audience, thank you again for coming back to another online seminar series presentation. And we see you next week. And well, Juan Pablo, maybe we see you at a conference. Yeah, soon. Yeah. Thank you so much for coming.
Thank you very much. Thanks, everyone.